All right, let's dive into something we use every single day but almost never actually think about. What is a number? I mean, really, you might think you know, but the answer is way more surprising than you'd expect.
You probably learned numbers before you could even read. They're everywhere. But what if I told you that our whole basic idea of what a number is kind of falls apart when you look at it too closely? And what if I told you that most numbers are actually completely unknowable?
Okay, so let's start with the simple stuff, right? The textbook definition. A number is just an abstract idea we use to talk about quantity or order. Seems straightforward enough. And for a number to be, a number, we expect it to have a few key properties.
First, it has to be unambiguous. 5 is always 5, no confusion. It's got to be abstract. The concept of 5 is different from 5 chairs or 5 cars. Numbers also need to be comparable, so we all agree that 7 is bigger than 5. They have to be workable, so we can actually do math with them. And finally, they've got to be representable. We need a way to write them down. These 5 rules feel like rock-solid ground, the foundation of everything. But what happens when we can't actually point to the number we're talking about?
This is where things start to get really interesting. I mean, think about algebra. We're constantly using symbols like x for numbers we don't even know. So if you don't know the number, can you still do math with it?
So check this out, because this is a really key distinction. On the left, you've got your everyday arithmetic. 5 plus 1 equals 6. You have to know what the numbers are to get a specific answer. But on the right, you've got algebra, and x plus 1 is just, well, it's x plus 1. We're not actually calculating anything. We're just moving symbols around according to a set of rules. The amazing thing is, we can do this without ever needing to know what x is. Okay, so let's take that idea and push it to the absolute most ridiculous extreme. What if we have a number that we can describe perfectly, but it's so unbelievably gigantic that we could never, ever hope to write it all down?
Take a look at this monster. We'll call it x. It's a power tower of tens stacked 6 high. The number this thing represents is so colossal. I mean, the number of atoms in the entire known universe is basically 0 compared to this. We can't calculate it, we can't write out the digits, but, and this is the important part, we can describe it perfectly with this little formula.
So here's the big question. Can we take this number that we can't even write down, our x, and do something simple like add 24 to it? It feels like that should be impossible, right?
And the answer is, yeah, totally. The result is just the description of x with a plus 24 tacked on the end. We don't need the value. We just play with the symbols. This is a perfect example of how a number's description can be way more powerful than its actual calculated value. But this leads us to an even deeper, weirder question.
You see, our giant number, as big as it was special. We cherry-picked it. It had a nice, clean formula. But what about the numbers that don't? What about just a regular, run-of-the-mill, typical number?
This question right here gets to the absolute core of it all. It turns out that numbers like 5, pi, or even that giant tower of tens are incredibly, incredibly rare. They're the odd ones out. The vast, overwhelming majority of numbers have no short description at all, no pattern, no formula, nothing.
To try and wrap our heads around this, let's try a metaphor. Imagine the number line is a huge, endless ocean. All the numbers we can actually name or write a formula for, the describable ones, they're like tiny islands scattered around this ocean.
But wait a minute. That metaphor isn't quite right, is it? The real number line is a smooth continuum. There are no gaps between numbers at all. An ocean with islands in it is by definition full of gaps, so that picture doesn't really work. We need a better one.
Okay, here's a much better way to picture it. Think of the describable numbers not as islands, but as lighthouses. They're these individual shining points of light. We can see them, we can name them, we can sail towards them. But they don't break up the ocean. They're just single points within it.
So, what's the ocean itself? All that water? Well, that represents the indescribable numbers. Almost the entire substance of the number line is made up of numbers that have no finite description. They are 100% mathematically real, but they are forever beyond our ability to name or even point to.
And this creates a huge paradox for us. Let's go all the way back to our original definition of a number. Remember? One of the core rules was that numbers have to be comparable. But if you can't even describe a number, how on earth can you compare it to anything else? So here's the conflict, laid out right in front of us. Our practical definition says a number has to be comparable, but the mathematical reality is that most numbers are indescribable, which makes comparing them impossible. So, does that mean that the vast majority of numbers aren't actually numbers?
Now, this feels like a contradiction that should just break math entirely, but it doesn't. The solution is just to make a really important distinction.
What we have to do is separate the idea of a number's existence from our ability to describe it. Mathematically, a number exists. It's a point on the continuum. It's a valid part of the system. The fact that we can't write it down is a limitation of our language, our tools. It's not a flaw in the number's being. The ocean is still there, even if we can only ever see the lighthouses.
This whole trip into the deep end of what a number is teaches us a really profound lesson that goes way beyond just math. It's about the very nature of knowledge and the incredible power of just admitting what our limits are. And this idea that a system contains things we can't fully get our arms around, it's not just in numbers. In logic, Gödel famously proved that any formal system will have true statements that it can't prove. In physics, quantum mechanics showed us that our everyday reality is just a useful approximation of something way, way weirder. In every case, the real breakthrough wasn't finding every answer. It was learning to accept and even work with the limits of what we can know.
So really, the big takeaway is this. Every definition, every system we create is a tool. It's a tool that helps us build a world that we can understand and operate in. But the very same act of defining, of drawing a line in the sand, also builds walls. It limits what we're even capable of seeing.
And that leaves us with this one last kind of mind-blowing thought. Our describable numbers, our lighthouses, they create the world of math we can use and explore. But that vast, silent ocean of indescribable numbers is still there. So it makes you wonder, if this is true for something as simple as a number, what other realities exist just beyond the edge of our definitions?